Welcome. Today we are going to start a new unit on absolute value functions. But before we delve into absolute value functions, we wanted to first start by remembering what we've already learned about transformations of functions and make some generalizations and sort of get our feet wet with a little bit of new and a little bit of old. The interesting thing about transformations is that they work the same regardless of what kind of function they're describing. In Algebra 1, we looked at linear equations for a considerably long period of time, and we learned that when you add to the end of a function, it moves it up or down, and if you multiply something, multiply it by a 2 or a 3, that it makes it steeper. If you take the function 1/2 x, it's less steep. So we learned about those in Algebra 1, and we also applied those same techniques to a quadratic parent function or to quadratic functions. And we learned that they can be moved left and right, up and down, and that you can make them really skinny. You can make them really wide, and then you can also flip them upside down. I believe we used a term like up like a cup and down like a frown. This year, we're going to start off by looking at absolute value functions. Absolute value functions are protected by the absolute value symbols, and we're going to delve into those and spend some time with those. But truthfully, the transformations that we talk about all year long are transformations that work on any type of function. This is what's called a piecewise function, and you'll look at piecewise functions in considerable depth when you get into pre-calculus. For all transformations, some general things can be to them, or to a specific function. We can multiply the function by a whole number or a fraction, giving us a vertical stretch or compression. We can multiply the x value of our function by a constant, and that will create a horizontal stretch or compression. We can add or subtract to the x value, creating a horizontal transformation left or right. And then finally, we can add to the entire function or subtract from the function, and that's a vertical translation up or down. I found one of my own typos. You'll find that I do this quite a lot, so I went ahead and fixed it there. Some important things to remember about transformations. Vertical transformations, or stretches, compressions, translations up or down will always change your x value. So if you make a t-chart, or if you look at a graphing calculator and you look at the y values are changed when you do anything in a vertical sense. Horizontal stretches and compressions, horizontal translations will always be changing your y values. Those are important to remember. And then the last thing you will hear us say frequently throughout the course of the year is that insiders lie. So if I am subtracting a 2 from my x value, that's really the same thing as moving it to the right. So instead of moving in a negative direction, it really moves in a positive direction. If I'm multiplying my x values by 2, I'm not really multiplying by 2, I'm really multiplying them by 1/2. So just keep in mind that insiders lie. And we'll look at that in a little bit more detail as we get some specific examples going. All right, let's look at some examples. I'm going to go ahead and tell you first, I've preloaded this with a few things because otherwise I think this lesson would take 342 hours. I apologize if we were doing some of this in person, then we could speak a little bit more in depth about some of the things that I'm going to talk about. But what we're going to talk about here is a vertical transformation. It's vertical because this is happening to the entire function. So this is vertical. That's something to keep in mind. And if I'm adding to my function, then that's going to move us up. And if I'm subtracting, that's going to move us down. It's because I'm always moving in a vertical direction. The specific example that's graphed here is f of x plus 3. So what this transformation is going to do is it's going to take this parent function, f of x, and it's going to move all the points on this graph up 3. So I'm just going to make a note here, up 3. That's what that does. It moves it up 3. I know that this is going to change my y values by adding 3 to each of the y values. So I can go through and recalculate. I can say -2 is my x value, plus 3 is going to give me -1, or I can just take my y values and add 3 to them. 1 plus 3 is 4, and so on. 0 plus 3 is 3. I can still substitute in here a 1. 1 plus 3 is 4. And that's how I can generate a table of values that I can use to graph, I moved my camera, to graph my new function. When I do graph the new function, grab something here to draw with, I can plot my points, my pairs, or I can look at this and say, oh, since this point was moved up 3, I move it up 3. And then likewise, move this one up 3, move this one up 3. And so whichever strategy you land with will work. Just want you to see that we are just vertically moving this graph up 3 points. And this becomes our new graph, which we are calling g of x. That's the new graph. It's the transformation of the function f of x up 3. When I look at my domain and range, we can write the domain and range in interval notation, inequality notation, and sometimes we can write it using some all real number symbology. There's also one called set build notation, and we'll talk about that a little bit more in the year. Domain for this function, because it has arrows on both sides, and the domain refers to my x values, I know that it can go on forever in the negative infinite direction and in a positive infinity direction. The range, however, is bounded. You'll notice that the lowest point on my graph of the original function is at 0, 0, and then my y values begin to go back up. So my range I would list as 0 to infinity, or you could just say that it's y values greater than or equal to 0, whichever one you feel more comfortable with. You'll find I use interval notation just because it's simplest for my mind. I don't have to worry about which direction my inequality goes or anything like that, but you do what's comfortable for you. My new function, the domain did not change because my x values did not change. So I can feel comfortable saying this is negative infinity to infinity. My range values, however, did change. Now, the lowest point on my graph is a positive 3, and I do touch it, and I still go up forever. So I would write my range as a 3 to infinity interval notation statement. If we look at the next one, our next example, the first thing I notice is that in this example, I am adding to the x value. This is inside. And so it's inside, it's worth noting, therefore horizontal. Horizontal. And because we know that insiders lie, in this example, it looks like I would be moving in the negative 2 direction or in a negative direction by 2. But what I'm really doing is I am going to add 2 to my x values. So if I'm adding, that is going to, if I see a +3 or a +4, that's going to actually move me to the left. And when I see subtraction, that's going to move me to the right. Because again, insiders lie, they do the opposite of fixed. With horizontal transformations, I'm changing my x values, right? So I'm going to put this again because it's important. Changes x's. So I am going to, instead of subtract 2, I'm going to add 2 to all of my x values. This becomes, I add 2, negative 2 plus 2 is 0. Negative 1 plus 2 is a 1, adding 2. And those are my new x values. My y values do not change. So I make no change to those. And then if I want to graph this new function, I move everything to the right. So my new vertex is going to be a 2, 0. Remember, the vertex is where your graph changes directions. So here's my new vertex. And then I have points on both sides. And what, I'm singing to myself here. So my new graph, pardon me while I draw poorly here. I missed a point, didn't I? This would have been, nope, I just didn't go through it. There we go. This one goes here. That's what it is. Okay, you get the idea. My graph looks something like that. This is a horizontal transformation to the right by 2 because insiders lie. My domain of my original function. We know for all quadratic functions, the domain is negative infinity to infinity for parent functions. My range, the lowest point, my vertex occurs at 0. I do touch 0, and I go upward forever. My new function, however, is going to have the same domain values. I still go in both directions forever. That doesn't change. My range is still the same because I did not move up or down. So that is the domain and range of my new function. So that's a look at some translations, left and right, up and down. Let's see what else we have in store. All right, the next graph that we're going to look at is a vertical translation, or it's a vertical transformation. And in this case, we're just working with a piecewise function. It doesn't have a particular parent function name that you need to know. We are going to look at vertical transformations. This is, I see that there's an a value in front of my function. That's because it's in front of the parentheses. That's what cues me to understand that it's vertical. And because this is a whole number, I'm going to be doing a vertical stretch by 2. What I remember with this is that because it's vertical, it changes my y values. And I'm gonna, when I change the y values, I'm gonna change them by a factor of 2. So I take all my y values, and this time I'm gonna multiply by 2. So I could take -6 and I could substitute it into my function, right? So if -6, 0 is the original, then I do something, and now 0 times 2 is my new y value, and that's going to be 0. -2 times 2 becomes a -4. This one is -4 also. 0 times 2 is 0. 1 times 2 is 2. So those should be my new y values because I multiplied by 2. And I can graph those. I actually cheated and went ahead because I tend to be a bit of a goofball and sometimes screw up the points when I'm under pressure, like I would be when I make a video. My new function should look like I took the y-axis, much like I could a rubber band, and I stretched it in a vertical direction. So my new function will look something like this. This is my new function, and my new function has the name g of x, so I'm going to label it. Forgive me if I forgot to do that on the last one. I sometimes just get so involved, I forget to do things. All right, my domain of the original function has arrows on both sides on the left and right, telling me that it continues in the negative infinity direction and towards infinity forever. It is the range values have a bottom. The original function has a bottom at -2. That is the lowest point on my graph, but it does go upward forever. So I would write my range statement as -2 to infinity, and there are lots of ways you can write this. Choose the one that's most comfortable for you. We did not change anything having to do with the domain, so my domain values stay the same. I'm using parentheses because you can't actually touch infinity. I use brackets when the point is actually a point on my graph, so that means I do touch that point. My new range value, however, in this graph is a little bit different because now the bottom of my graph is at -4. So I'm going to say that the -4 is the lowest point on my graph. I go upward forever, can't touch infinity, so I give it a parenthesis. What happens if that's a fraction in front of my function? Well, if there's a fraction, a number between 0 and 1 in front of your graph or in front of your function description, then this is vertical because it's in front of the function description. And we are going to again change the y values. This particular one is a vertical compression by 1/2. It's as if I compressed everything vertically, making it really flat. I'm going to change the y values, and I do this by multiplying by 1/2. Vertical translations and transformations are pretty straightforward. I take 0 times 1/2, That's 0. -2 times 1/2, -1. Half of -2, half of 0. You have nothing. You can't give half. Half of 1 would be 1/2. That's a strange one, but very plottable. Once I have my new ordered pairs, then I can graph them. And again, I went ahead and cheated and gave myself some hints so I can actually do this in the right way. Although I probably will manage to mess something up eventually. Okay, so here's my new function, nicely graphed. I'm going to refer to, it's a bad arrow. I'm going to remember to label this. Graph is g of x. Guys, the g is just a different representation. You can use your initial. You could use d of x, c of x, m of x, whatever floats your boat there. We've already talked about the domain and range of the original function. My new function, again, the domain is not changed. I'm still going to stretch from infinity to a negative infinity. My range value has changed, however. When I do things vertically, that often changes my range. In this case, the lowest point on this graph is at -1 now, but it still continues upward forever. So my range is -1 to infinity. Important thing about this page, folks, the manipulation that we are doing is happening to the function description. It's outside the function, therefore it's a vertical transformation, and it will change our y values. Next, I want to just do a quick segue and show you the picture of a cake that was given to one of my cousins. The first thing I noticed about this cake is that her name is Ann Lewis, not Al. The second thing I noticed is whoever was creating the cake couldn't really differentiate between what was supposed to be on the cake and what the instructions for decorating the cake would be. Thought I would share that with you just so you could have a momentary chuckle between transformations. All right, for this next table, don't you love all these tables? For the next table, we are going to look at functions in the form of f of b of x. And in this case, the number is inside parentheses. That's important, folks. It's inside brackets or grouping symbols. It could be absolute value symbols, inside parentheses. It could be inside a radical, inside absolute value symbols. These are all different kinds of grouping symbols. And when I am inside a grouping symbol, then I know I'm doing something in a horizontal manner. In this case, this is a horizontal compression by 2. And what it's going to do is it's going to change my x values, changes my x values, and it does the opposite. So instead of multiplying by 2, I'm actually going to multiply my x values by 1/2. My y values stay the same. So here again, this is just kind of a silly piecewise function. It's not one that we are going to study in depth, but it is a function. So I have these points, I have my x values and y values, and because I'm doing a horizontal compression, I'm going to actually, and pardon my scribbles here, I somewhere along the way filled in x values when I really should not have. Okay, so I am going to change my x values, and I'm going to do the opposite of multiplying by 1/2, which is multiplying by its reciprocal. So I'm multiplying by 1/2 instead of multiplying by 2, sorry. So I take half of -4, and that gives me -2. Half of 0 is going to be 0. Half of 2 is going to be 1. Half of 5, that's 5 halves. Half of 6 gives me 3. So these are my new x values. Horizontal changes x's, vertical changes y's. I changed my x values, and I did the opposite. I did the inverse. The inverse, I multiplied by 1/2 instead of a 2. So when I connect all these lovely points, let's just go crazy and hope I can do this correctly. The pressure. Okay. I think it looks something like this. And this one's going to go down. All right, we're going to go with this. For expediency, I'm copying off of one I did last year. I might have missed something, but I feel like that's the general idea. This is my new function. In this case, it's called g of x. We're not very original with our transformation names. It's okay, we'll have plenty of room for originality later. My domain for this function is negative infinity to infinity. It has arrows on both ends, and my transformation does not change that. My range is still bounded by, it goes down forever. And remember, when doing range statements, you always put the smallest value first. It goes down forever. So negative infinity is where I'm trying to reach in the lower bound. And the top of my graph, the very highest point I touch is at 2. I do touch it, so I use a square bracket. And the range statement for after this transformation has not changed. So we can just go with that. And then as unexpected as multiplying by 2x is when I do a horizontal compression, the next one I look at, horizontal stretches, is equally strange. In this particular case, this is when the b value, the thing I'm multiplying by, is a fraction. It's a number, well, it is a fraction or a number between 0 and 1. Fractions can be bigger than 1. I misspoke. If I look here, I'm multiplying all the x values by 1 over 1/2. It's horizontal because I am protected by a grouping symbol. I'm changing the x values. Notice I did the table right this time. So I'm going to change my x values, and I'm going to multiply, and this is going to look weird, guys. I'm going to show you a better way to think of it. I'm going to multiply by 1 over 1/2, which is just weird. Or that's the same thing as multiplying by 2. Multiplying by 2 is much easier on my brain. I'm multiplying by the reciprocal. I'm good with that. -4 times 2, -8, 0 times 2, 0, 2 times 2 is 4, 5 times 2 is 10, and 6 times 2 is 12. Right? So I just multiply by 2. I can't graph all those points because my x values, this little graph, is just not big enough. In fact, it's not really big enough for me to do even the few I have plotted. I can graph -8, -2. I can graph 0, 0. I go up to over 4, up 2. So that would be my next point. 10, 2, and 12, 0 just really don't fit on my graph, but I know that it's going to go off in that direction for a bit. And it's going to continue towards negative infinity in the x direction. And this is my new function, g of x. And what I've done is I have just stretched it in a horizontal direction. My new function, the domain, is still negative infinity to infinity. My range has not changed either. Blessed changes there. All right, folks. So those are by far and away some of the most confusing transformations that you can do. The ones we're going to look at next, I feel like y'all are fairly familiar with. The nomenclature might be a little bit different, but I suspect it's going to look safe and familiar. When we change the sign, or when we multiply by -1, this is what we call a reflection. So a classic example is, and pardon me, I'm just going to write right here. The classic example is when you have a parabola and you flip it upside down, and that's a reflection, and he just becomes this lovely flipped drawing, right? So hopefully you can remember that from your previous algebra class from years gone by. Because the negative in this case appears outside the function description, I know it's a vertical reflection. It's going to be reflected over the x-axis, because if I think about flipping something vertically, this is the line that controls that. It's a vertical transformation, so my y values change, my x values stay the same, but it's like multiplying all of my y values by a -1. So I just change the signs. The simplest way to think of it is just change your signs. Multiplying by -1. When I do that, my graph actually just flips upside down, and it looks a bit strange. Here again, I cheated and made some points ahead of time. It really is in everyone's best interest when I do that, because holy cow, graphing is a challenge for some people like me. I also shouldn't sing. There we go. That's my flipped function. Flipping is fun, right? So that is my new function. And the domain and range of my original function can be seen here. When I do a vertical translation or transformation, I am not changing my domain values. So the domain is going to remain the same. In this case, however, where before I was going down forever towards a negative infinity, how do you say that? Towards negative infinity. This time I'm actually going up forever. So my range statement just basically flips. Now my lowest point is at -3, and I'm going upward forever. The last transformation that I'm going to show you, and one that we actually don't look at too frequently in Algebra 2, is a horizontal reflection. I know it's horizontal because it's happening inside the grouping symbols. Again, I am going to be multiplying by -1, and I remember that horizontal transformations are going to change my x values. So notice I went ahead and put my y values because those don't change. I'm changing my x values, and I'm again going to multiply by -1. This will reflect me. I'm flipping over in a horizontal direction, and I'm flipping over the y-axis. If I multiply my x values by -1, then the signs change, and I can graph these. I have some points. I'm going to go ahead and just, this terrified. Okay, that does look right. I just never know. This may or may not have been created correctly. Take it on faith. This should be my new function. Let me check. I went over 1, down -2, 0, 0, -2, +2, -5. I think I actually did it. There we go. So that's the graph of my new function. My domain, again, I have arrows both ends of g of x, telling me I go from -infinity to infinity. My range did not change. So my range is still going to, my graph still continues downward forever. And the highest point on my graph will continue to be +3. And I do touch it, so I use a square bracket. Summary, folks. You can keep this table close to you. Learn it, memorize it, come back to it frequently throughout the year. It gives you examples of all different kinds of functions that can be used and what those transformations might look like. The important thing that we have talked about today is that it is actually an order that matters when doing transformations. So when you're describing transformations, always describe the horizontal transformation first, horizontal translation. The second thing we describe are stretches or compressions, and they can be vertical or horizontal. The third thing we talk about when ordering a set of transformations is the reflection across either axis. And then lastly, we do vertical translations. This can sometimes be difficult to remember. It's a particular order, and it actually matters, and I look for it in all my answers. The way that Ms. Lowry once introduced us to just an acronym to help us remember, or there's a word for this, but horizontal, stretches and compressions, reflections, and then our vertical translations. Harry Styles rocks V-necks. Silly, I know, but if you can remember that Harry Styles rocks V-necks, you will always have a built-in cheat sheet that helps you remember what the order of transformations needs to be when describing them. Thanks for your attention today, folks, and I will see you again soon.